wrote it like this. And we spent some time on Gauss' law, right? We wrote it like this. So, the main message of Gauss' law is that with these equations, the thing on the right gives rise to something on the left. So, Gauss' law is basically saying that electric charges produce electric fields. Yes? And then you can talk about the details of, if it's a positive charge, electric field is away from the charge, and if it's a point charge, the magnitude turns out to be k cubed r squared. If it's a negative charge, the electric field is pointing towards the charge. You can get into those details, right? But at the fundamental level, what this is saying, right, if you think of the thing on the right produces the thing on the left, this is saying that Q stands for electric charge, and electric charges give rise to electric fields. That's it. And this circle means you consider, and this is a surface integral, right? So you consider a circle means it's a closed surface. You consider a closed surface, so E dot dA over that closed surface is related to the charge inside of that, right? So we talked about Gauss' law. If you write the same equation with a closed surface integral, and you replace the electric field with the magnetic field, this turns out to be 0. In other words, if you replace Gauss' law, if you replace in Gauss' law the electric field with the magnetic field, the right-hand side turns out to be 0. This is, this equation has no name. Some people call it, Gauss' law for magnetism, but, there's really no name. So, remember, the thing on the right produces the thing on the left. So, over here, electric charges produce electric fields. So, if there were something on the right-hand side of this equation, we would call that magnetic charge. So, then we would say magnetic charges produce magnetic fields. But, mathematically, this equation has a 0 on the right-hand side. So, the message is that there are no magnetic monopoles, no magnetic charges in nature. That's what this equation is saying at the most fundamental level. Electric charges produce electric fields. Magnetic fields are not produced by magnetic charges. That's what the second equation is saying. There are no magnetic charges in nature. And no one has found a magnetic charge in nature yet. If somebody finds one, then the books will have to be rewritten. Correct. That would be like, wow, that should be a Nobel Prize by the end of the year. But, as far as we know, there isn't. And there are people working to, discover magnetic charges, but, they just haven't succeeded. And maybe they'll never succeed. We don't know, right? As scientists, you have to be open to, new discoveries and shaking what you think was a complete theory when it might have been just incomplete, and embrace the new, the new theory that, of course, has to be supported by data, right? The ultimate judge of any theory is experimental data. You need that verification, because otherwise it's just a theory, or maybe philosophy. Anyway. So then, Michael Faraday wrote this equation, right? And I'll write it in the language of electric fields, right? So he wrote, like E dot something, but instead of a surface integral, he wrote a line integral. So you write a circle, because now you consider a closed loop. It's going to be a line integral, not a surface integral. And you replace the electric field. Now instead of an area, because if I wrote an area over here, then I'm back to Gauss' law. So this is dl or ds. And what he discovered is that this is minus d dt of magnetic flux. But magnetic flux, how do you define magnetic flux? It's B dot dA, not a closed surface over here, right? Because if I put this over here, then this by the second one, that's 0. Right? So it's not a closed surface. It's just this is B dot dA over the surface for which the boundary of that surface is this loop over here. So this is just that.
Shouldn't D have an arrow over it to be like since it needs to be a vector for the dot product?
What's that?
Shouldn't dA have an arrow over it?
Yes.
Because you need two vectors for the dot product?
Yes, correct. So this is Faraday's law. Now, if you write, notice, electric field, surface integral. Magnetic field, surface integral. These two. Now here we have electric field, line integral. So what if I write magnetic field, line integral? In other words, so that these two equations these are two surface integrals, these are two line integrals. Right? One for electric field, one for magnetic field, one for electric field, one for magnetic field. What is this? What do we know so far? What is this equal to? Do you recognize this?
Mu naught I.
Mu naught I, exactly, which is Ampere's law, right? Yes, that's chapter 28. You were tested on that. So this is the way it is. This is Ampere's law. Yes? So the message here is this. And what is I? It's dq dt. A flow of charge. So what this equation is saying is that electric charges in motion generate magnetic fields. Moving electric charges generate magnetic fields. Faraday's law is saying that like a time-changing magnetic field, can give rise to an electric field. Here, magnetic fields are produced by electric currents. But what is an electric current? It's just a flow of electric charges, right? So, moving electric charges generate magnetic fields. Now, this equation, if you remember how I wrote it in chapter 28, I said magnetostatics only. So that means the currents were the same, like 5 amps, 5 amps, 5 amps, 5 amps, 5 amps, 5 amps, 5 amps. Because, and there's also another problem that comes up, and I like to make you aware of that problem. So let me just bring this to your attention. In other words, this equation is incomplete. It's good in certain conditions, if certain conditions are satisfied. If those conditions are not satisfied, it's incomplete. There's something else that we don't know about. So it's incomplete. So consider the following. And again, I'm going to use the board. To pose this problem. What if we consider a capacitor being charged? You did an experiment on an RC circuit and the capacitor was charged. So, this is like plate, wire. So, except that this plate over here on the left is this yellow circular plate, seen from a side. This plate over here is this other yellow plate, right? You got a vacuum in between. Right? And you have current coming this way. And, you got current that way. And the capacitor, the plate on the left, gets positively charged. And the other one gets negatively charged. Essentially, saying that the current is to the right over here, you're saying that free electrons are going this way. And then they begin to pile up over here and make it negatively charged. Right? And saying that the current is this way in this part of the wire over here, right? This means that the free electrons over here are going the other way, right? And as they leave, there will be an excess of positive charges left behind in this plate, right? And then you charge the capacitor. Suppose that I consider this wire with this current I, and I want to know the magnetic field here, right there. What would be the magnetic field generated by this current in this wire? Let's think it's a long wire at a distance r from this, right? So what we did in chapter 28 is we said, okay, let's use Ampere's law. And when we use Ampere's law, we said, okay, let's consider an Amperian loop. An Amperian loop like this, right? So we said this is an Amperian loop, AL. And we wrote this, Ampere's law, right? And we wrote B dot dl equals mu naught I enclosed. So this becomes B, the L is 2 pi r, and this is mu naught. And what did we say is I enclosed? Right? But what does I enclosed represent? What is the definition of I enclosed?
The current.
The what?
You said earlier dq dt.
Right, earlier today, but when I write I enclosed in Ampere's law, what does I represent?
The current passing through the cross section of the loop.
Okay, so I have to be more careful now. So I have the loop, the Amperian loop. So I is the current passing through the surface whose boundary is the Amperian loop. The surface whose boundary is the Amperian loop. So in chapter 28, the easiest surface that's bound by the Amperian loop is just a circle, right? So that surface, the plane, the surface, right, is on the plane of the loop. So we just said, we said this. Oh, it's the current through that, right? And that's just I. And then we said B equals mu naught I over 2 pi r, right? And that's the answer. And that's correct. Now, what if instead I did this again? So this is B times 2 pi r, same Amperian loop, right? Same Amperian loop. And now I decide that the surface that's bound by the Amperian loop is instead a surface like a balloon, like this, that goes like that. Imagine you're gonna blow a balloon, right? You're gonna put air in the balloon, and you go, you got a little, that aperture over there is the Amperian loop. And the balloon is the surface that's bound by the aperture. But in this case, what is the current through this surface? Nothing, because the electrons come in, they stop over here, and they induce these electrons to go away. So the electrons come in, stop. It's like they yell across this and say, hey, you guys, keep going. And then the other electrons from here end up going. So right through the loop, the current is 0. So if I do it like that, this is inconsistent with that. And we have a problem. The correct answer is this. But if I choose that other surface, from the mathematical definition of, this current being the current through the surface that's bound by the Ampere loop. So, we have a problem here. And what happens over here is that as the charges are piling up, see, this current is not constant. As the charges are piling up, the current is going to be changing. And so we are outside the magnetostatics issue. So that's why using Ampere's law, in this case, if I happen to choose that surface, I get the wrong answer. If I choose this as the surface bound by the Ampere loop, I get the right answer, but if I choose that surface, I get the wrong answer. So this is where Maxwell, James Clerk Maxwell, came along. This was in the 1860s. And he came along, Scottish, he was from Scotland, and he said, we have a problem over here. He said, how do we fix this? So he said, well, Faraday, who wrote this in 1831, and that was in the 1860s, so that's like, over 30 years after Faraday. Maxwell says, Faraday taught us in 1831 that a time-changing magnetic field can give rise to an electric field. I wonder if nature is symmetric enough such that if a time-changing magnetic field can give rise to an electric field, I wonder if a time-changing electric field can give rise to a magnetic field. Just, is that possible? So what he did is he went ahead and just, did this just a guess, and try to play so that the units came out right. And he ended up writing this equation, or this expression, mu naught, and then epsilon naught, and then just like a time derivative over here, d dt of an integral, but he replaced b by e, that dA. So he wrote that instead. He just, in other words, he corrected Ampere's law so that it wouldn't just apply in magnetostatics, so that it would apply all the time. So this is Ampere's and Maxwell, because they both separately contributed to this. Ampere came first. He just modified. So Maxwell, so this term over here was, introduced by Ampere, and this one by Maxwell. So if we solve this problem again using this surface, like a balloon-shaped surface, so that that surface, the boundary of that surface is the Amperian loop, right? If we do that, then we would say plus mu naught epsilon naught d dt of E dot dA. And so we would have B times 2 pi r. First of all, the current through this surface I enclosed is 0. So therefore this is out. This is, this is 0, that's good. But then we have plus mu naught epsilon naught d dt of, now, that will be the electric field through that surface. It will be the electric field through the surface. And since this is positively charged and this is negatively charged, there is an electric field set up this way, right? As the plates get charged, there is an electric field set up to the right. And what is the electric field between a set of parallel plates? Do you remember? Sigma, the charge period area, divided by epsilon naught. Due to one sheet, it's sigma over 2 epsilon naught. But due to the two sheets, each one contributes half of sigma over epsilon naught. If you look up your Gauss's law from, chapter 22, a long time ago, in this course, then it's this. But what is sigma? This is the charge per unit area in the plate. Sigma is the charge per unit area, right? And then you have epsilon naught. So then you have Q. And if you take the derivative of this with respect to time, what will it be? Well, the area of the plates are the same. Epsilon naught is a constant. Then it will be dq dt. But what is this? What is the rate at which the charge in the plates of the capacitor is, changing? So the rate at which the charge in the capacitor is changing, right, is this current I. I is dq dt. So then this is just the current in the wire. So the E dt is I over A epsilon naught. So I can think of this derivative, right? What's the area of this surface that I'm imagining over here is not changing. I'll just keep it fixed. What's going to be changing is the electric field, because as charges accumulate on this plate and this plate, this electric field is getting stronger, stronger, stronger. So this derivative with respect to time is acting on this guy. So this will be mu naught epsilon naught, and then the integral of the E dt times the area. But this guy over here is this. So this is 0. So this becomes mu naught epsilon naught integral of d dt, which is the current, over A epsilon naught times the area, right? I'll just write it like that. Notice that this cancels that. So I have B times 2 pi r equals mu naught I. I can pull out the A, and then I have the integral of this area. But the integral of this area is just the area, and then that's going to cancel this, and I recover. So I get that B equals, I get the same result as what I would expect if I chose the area bound by the surface bound by this Amperian loop to just be the flat surface. So then I have consistency between this and this. So, this was just this, right? The question is this true? It fixes this problem over here, right? What's more striking was the next step. Then Maxwell came along, and by the way, these 4 equations are known as Maxwell's equations. Even though, remember, he had nothing to do with the first equation. He had nothing to do with this equation. He had nothing to do with Faraday's law. And he had half to say about Ampere's law. He modified the 4th equation by adding this term. His contribution is this term over here. Ampere contributed this was Faraday, this one doesn't have a name, and this is Gauss. So even though Maxwell only contributed this part, half of the 4th equation, people call this Maxwell's equation. But what's interesting is then he took these 4 equations, and I guess he manipulated them. Well, I don't guess, I know. He manipulated them, all of them, so he was working with all of them, and I guess that's why they call them Maxwell's equations. But again, his credit really is to this one. But he then manipulated these equations, and he was able to show that the electric field and the magnetic fields, the electric fields and the magnetic fields in these equations satisfy these equations. He took just imagine an x-axis, and he was able to show this. The second derivative of the electric field with respect to, let's say, x equals, what is it? Mu naught, epsilon naught, second derivative of E with respect to time. And second derivative of the magnetic field with respect to position equals mu naught, epsilon naught, second derivative of the magnetic field with respect to time. So he manipulated these four equations, which only he could do. Do you know why he's the only one who could do this? Because he's the only one who knew this term. He added the term and then started thinking about it. By just saying, because a time-changing magnetic field can give rise to an electric field, I wonder if a time-changing electric field will give rise to a magnetic field. Just wonder. And he played with them, and he got to these equations. And at this point, he must have fallen off his chair. Assuming he was sitting on a chair and working on it, and it must have fallen down. Because he recognized this as the second derivative of some function, let's say with respect to space, is 1 over v squared. Second derivative of that function, except that that function here is the electric field, that function here in this other equation is the magnetic field with respect to time. He knew that this equation describes a wave. A wave where y is the quantity that's oscillating with time, and the v of here represents the speed of the wave. So as soon as he saw these equations, he said, oh my goodness, they look like a wave equation. And then in vacuum, right? So then he says, oh, all I need to do is take this and compare it to this, right? It's the same factor in both cases. So then he did that. At this point, he must have been rushing. But then he says, okay, 1 over v squared therefore has to be epsilon naught mu naught. This means that vacuum supports the propagation of electromagnetic waves. A wave that consists of electromagnetic fields. Let's see how fast these waves, electromagnetic waves, would propagate in vacuum. He didn't know what the answer was. But, so then he said, okay, v will be 1 over the square root of epsilon naught mu naught. And he didn't have a calculator, but those people were good at doing these things, and he knew the value of epsilon naught and mu naught. And then he went and did, okay, so epsilon naught is 8.85 times 10 to the minus 12 for vacuum, right? That's the electric permittivity of free space. And mu naught is the magnetic permeability of free space, that's 4 pi times 10 to the minus 7, and no calculator, so he did this. And to his surprise, he got 10 times 10 to the 8th meters per second. And this is when he fainted. He must have fainted at this point, because he recognized that speed to be the speed of light in vacuum. And up until this term was written, people didn't know what light, or they didn't know much about light. They knew some things, but there were various questions. There still are some questions about light, but one thing that was troubling in the 1800s is that people have conducted experiments with light, and light exhibited behaviors of interference, constructive interference, destructive interference, diffraction as it went through small slits. Those are all phenomena associated with waves. So light is a wave, but gee, what kind of a wave is it? Right? If it obeys a wave equation like this, something is oscillating, right, in space as time goes on. But gee, light can travel from the sun to the earth, and we know that because you can see the sun, right? During the day, you go outside, you see the sun. But what's between the sun and the earth? Vacuum, empty space. So if light is a wave, right? Because of all of these experiments that show that light behaves as a wave, diffraction, interference, those are all properties of waves, then what kind of a wave is it? Because if there's a wave, something has to be vibrating. Something has to be changing with time and vibrating. But in vacuum, since light can travel through vacuum, but vacuum is the emptiness of space, then what's vibrating? So it's like,
Isn't it a particle and a wave at the same time? Or light?
But that was another idea
okay.
that came up later. And so by him saying that a time-changing electric field is associated with the generation of a magnetic field, which is the reverse of what Faraday had said, that a time-changing magnetic field can give rise to an electric field. So then, by adding this term over here, he was able to think of an electromagnetic wave or light as an electromagnetic wave. I mean, what are the chances that light travels at this speed in vacuum and that an electromagnetic wave will travel at that same speed in vacuum? The conclusion is that light has to be an electromagnetic wave, right? There's no way out of that, right? But if light is a wave, something has to be vibrating. So what's vibrating? So what Maxwell discovered is that what are vibrating is nothing actually, no material particles are vibrating. What's vibrating are the electric and the magnetic fields. As the electric field vibrates, it gives rise to a magnetic field. But because this is changing, the magnetic field is changing. But if the magnetic field changes with time, it gives rise to the electric field. Which changes with time gives rise to the magnetic field. Which changes with time gives rise to the electric field. Which changes with time, and so they regenerate one another. And then they can propagate through vacuum. So James Clerk Maxwell in the 1860s was able to unify, people in those days thought that magnetic properties, Faraday showed that magnetic properties can be related to electrical properties, but for a while people thought, electrical properties, electric behavior is one thing, magnetic properties is another thing, and then optics, light, is just another field. And he was able to unify these three fields, electricity, magnetism, and optics. Now you can talk about electromagnetism. Optics being, associated with the theory of electromagnetism. Later on, in 1900, Max Planck said, if you consider the radiation emitted from the surface of an object by virtue of the temperature on the surface of the object, then it seems like objects emit radiation in little bundles of energy. But at the time, in 1900, when Max Planck from Germany made that statement, people were convinced that light was a wave. With this theory over here, then people said, okay, light is a wave. For sure it's a wave. It's an electromagnetic wave. This was the 1860s, 1870s, right? 30 years later, Max Planck comes along and he says, if I look at the theory of the emission of radiation from the surfaces of objects, it seems like objects emit in little bundles of energy. In little, like little squirts of energy. Little packets of energy. Which then became known as photons, particles of light. And he says, well, I don't know what's going on, but if we think of the radiation as being emitted in little bundles as photons, then I can write down a theory that can explain this phenomenon of, radiation emitted from the surfaces of objects. And why does it do that? I don't know. It's got to be something related to the mechanism on how objects emit radiation. 5 years later, Albert Einstein came along and he said, Max Planck taught us that, when you consider the radiation emitted from the surface of an object, the radiation is emitted as photons, although the word photon was not introduced until the 1920s by some chemists. But, in bundles of energy, packets of energy, Albert Einstein said, you know what? Electromagnetic radiation is composed of photons. And then there was a big uproar, and he faced a lot of opposition to that idea. No, how could you say that? Look, light can, diffract. It can have interference effects. So light is definitely a wave. Maybe that problem over there, something's going on that we don't know. But you can't just state that light, by its own nature, is quantized into these, bundles of energy called photons. And he met a lot of opposition, and so on. So Albert Einstein was able to have a lot of arguments with people over that over the years. But what he had in his favor was that there was this problem having to do with the photoelectric effect, where in the photoelectric effect, you have a metal in some vacuum, and you shine light on it, and then electrons would be emitted from the metal. They would just come off the metal, depending on the frequency of the light that was used over here. And so this actually was a problem that had not been solved. In the last 20 years of the 1800s and the first 5 years of the 1900s, this was a problem that was calling out for a solution. So it was kind of an interesting problem. If the frequency of the light is low, then electrons never come off the metal. And so people thought, oh, okay, to get electrons off the metal, you gotta give them enough energy so they come off the metal. So what happens if we make the light more intense? But the same frequency, same color, right? Same frequency, same color. Let's say this is red light, right? Just focus the red light, send in more energy, and then electrons should come off. They never came off. But then they increase the frequency of this light. Let's say they use blue light, let's say, so make the frequency is now high. And then electrons would come off the metal. And then they noticed that if they increase the intensity of the blue light that managed to emit electrons from a particular metal, they said, okay, let's focus the light, let's make it more intense so that the electrons come out with more energy. Because they could measure the energy of the electrons emitted. And so they increased the intensity of the light, and the electrons didn't come off with more energy. What happened is that more of them came off. More electrons came off, but they didn't come out with more energy. So that was a problem. And people were writing down a theory to explain this photo, light, electrons emitted from the metal. People were writing down a theory to explain the experimental data, and everyone failed. Everyone failed because everybody was thinking of this light shining on this metal as an electromagnetic wave. And Albert Einstein took a different approach. He said, okay, you guys are all failing? All right, let's try this. How about if we think of this light as a stream of particles, like Max Planck told us in 1900, when describing the emission of radiation from the surface of an object. So let me take another approach. Instead of thinking of this as a wave, let's think of this as particles of light. And Max Planck had said that the energy of each one of these photons is proportional to the frequency of the wave description of the light, and the constant of proportionality is called Planck's constant. So it's the energy of a photon that would be used to describe the wave as a stream of particles, and it's associated with the frequency of the wave description of the light, right? So Max Planck wrote this in 1900. And Einstein said, I'm going to borrow Planck's equation, and I'm going to write down a theory to explain the photoelectric effect. And my goodness, he was able to explain every feature associated with the photoelectric effect. He says what happens is that, for example, suppose the energy that's necessary, suppose this is some metal. Suppose the energy to get the metal, this is energy, not electric field. Suppose the energy necessary to liberate electrons, the minimum energy, suppose it's 3 electron volts. And if you consider, for example, something like red light, the energy of a photon of red light is like 2 electron volts. So Einstein said, of course, you never had success shining red light onto this metal. Because if you think of the light that's made up of photons, then each bundle of energy has only 2 electron volts of energy. And when an electron absorbs 2 electron volts, it's not enough to get them out of the metal. They need at least 3 electron volts. And of course, when they made the light more intense, they thought, oh, we're putting in more energy, at some point the electrons will come out. He says, by making the light more intense, you're just sending in more photons. But it's because the same color, same frequency, if every photon still has only 2 units of energy. So it's not going to make them come out of the metal. Now, if you increase the frequency of the light, let's say you make it violet light, for example. Do we have violet somewhere in here? Not really. But let's say you send in violet light, because the frequency is higher, the energy per photon, let's say, could be 3.2 electron volts. And then Einstein said, with the higher frequency, if these electrons need 3 electron volts to get out, if we give them 3.2, they're going to come out. And of those 3.2 electron volts coming in, 3 are going to be used to get out, and when they come out, they're going to come out with the remaining energy, 0.2 electron volts of kinetic energy. And by making the intensity of the light bigger, what you're doing is you're sending in more photons, but still with the same energy. So if you have more photons coming in, you're going to get the more electrons coming out. So he was able to explain every question that people had associated with the photoelectric effect. And he made the statement that light by itself is quantized into these bundles of energy, which later on became known as photons. But then he made a lot of opposition to that idea, even though he was able to explain the photoelectric effect perfectly. Albert Einstein was awarded the Nobel Prize in Physics in 1921 for this work, for the photoelectric effect. That was the only award that he got from the Nobel Committee. He's most famous for his theory of relativity. Never won a Nobel Prize for the theory of relativity. He predicted the existence of black holes, which have been detected. In his theory of relativity, he predicted the existence of gravitational waves that travel through space at the speed of light. Well, they were detected in 2015. But Albert Einstein died in 1955. They don't give Nobel Prizes to dead people. So he missed out. The experiment to confirm his theory just was done after he had passed. Right? He wrote a formula on time dilation, and the time dilation was verified in around 1970 or so at Harvard University. But again, he died in 1955. So, and by the way, the time dilation formula that he wrote in 1905, it's what is used to make the GPS system work. So people, when they started working on the GPS system, right, to pinpoint your location on the ground, they didn't use Einstein's, time dilation equation because, it's not necessary, they thought. And then, you would be here and it would say that you were 2-3 blocks away. It just wasn't working. And so they said, well, okay, let's use Einstein's, equation, let's see what happens. Boom. Nowadays you drive, it's like, turn right, my goodness, it's like there's another exit that it pinpoints your location more accurately. Right? He could have won another Nobel Prize, right, for the use of the GPS, of his equation of time dilation in the GPS. Right? Einstein in 1917 wrote a theory that talked about stimulated emission of radiation. How atoms can emit radiation. You talk about some of these topics in Physics 285, and he says that atoms can be stimulated to emit radiation. Atoms, when excited, you just leave them alone, just cross your arms and just watch them, and on their own, in due time, very quickly actually, like 10 nanoseconds or so, they'll emit radiation out once they have been excited. But there's no way to predict in which direction the radiation is going to be emitted, or exactly at what specific instant of time in a short time interval they will be emitted. And Einstein said, well, we can stimulate an atom to emit when we want it in the direction that we want it. And not only that, in phase with it, also like constructive interference. Well, stimulated emission of radiation, you have a photon coming in, say like that, you have an atom that's excited. Let's say the electron is here, it can jump over here, and if the energy of this photon is the same as this energy difference, it's like this photon comes in and it's going to talk to the atom and say, emit now. And then this photon is not absorbed, it just keeps on going through. And then it causes the atom to emit, and now this one emits, and emits in phase with the one that was coming in. So now you got 2 photons instead of just 1 photon. Now you have 2 photons over here.
Wait, is a photon an electron?
No,
It's just like a bundle of energy.
a bundle of energy.
Oh, okay.
plus the atom, which is now in the ground state. By having the electron jump from here to there, it lost energy. That energy goes into this photon. The other photon doesn't get absorbed, it just goes through. So that was the original photon. But the point is that you have one photon coming in, and now you have two going in the same direction. So that's light amplification.
Is it only when the electron drops to the ground level that it releases a photon?
That what?
Is
That it emits the photon, yes.
Okay.